Thank you very much. So first let me tell you how this originated. Dr. Doshi, who was a chief scientist at CERDEC, specifically in the Space and Terrestrial Comms Directorate there, is a longtime player in MILCOM, and he had the insight that with all the recent interest in robotic systems from the top down, why not try to interact with the communications community through a panel session, and based on the level of interest shown, we would then next year go to a full paper session if that's deemed appropriate. So in this endeavor, it's been a team effort between Dave Scheidt from APL, right over here to my left, and me. And it's part of a two-panel intentional system, really, of information presentation. The first panel took place yesterday, and that was kind of laying the groundwork for what are the motivations for getting interested in autonomous systems. You know, what are the people who've had lots of field experience see as the payoffs and the challenges in this area. And we actually kind of turned the tables on the audience and asking them, you know, what technologies they had encountered that they thought could help us out of some of the predicaments in terms of info security, the sensitivity to latency that you have if you're in the teleoperation world, and also in that same world, which is kind of the Army's state-of-the-art in fielded systems. You have the huge bandwidth requirement in the downlink for full video. So they related their experiences in areas such as unmanned underwater vehicles, tunnel work, looking to use robots to explore tunnels, both for civil and military applications, and just a wide spectrum of different types of interests in the area, and spectrum management was one of them. So we think we convinced ourselves that there was a huge opportunity here, kind of a two-way opportunity, where we definitely need help in the communications area and these other areas as well, the networking and the cyber protection, for these systems to ever really function big time in a major league fielded way. As I said, at OSD and above, there's a great deal of interest in this for several reasons, and the minutes of the charts that were briefed yesterday that you'll get a copy of describe all of that at a relatively high level of detail, but the POC information is in there as well. I understand you'll be getting that in about 3 weeks. So in this panel, rather than the broad motivations, we are picking particular technology areas and drilling down a bit in them. We don't have the time to go too far, but we have a group of technologists here who are very familiar with quite a broad array of technologies that are useful for a variety of different kinds of applications in both industry settings, and the primary interest is in the military setting. So the objective for today is really to stimulate questions from you as to technologies that you might see here that either you were not familiar with or you weren't familiar with in this context, and give you a taste of sort of the major challenges we're facing, and hopefully tap into the audience either real time or for proprietary reasons later in the game about ideas you have that could really help us enormously, which we're going to need in this technology area. The whole introduction of autonomy it provides it's a two-way street, actually. It provides an opportunity for us to benefit greatly from the comms community, and in the other direction, it provides the communications and networking community the ability to place relays, things of that sort, autonomously just by clicking on a map where you want the system to go, and it will go there. We had the first demo of that kind of technology, a field experiment, last November up at Fort Dix, and it worked quite well. So without further ado, I'd like to introduce Dave Scheidt. Dave is a long-time APL person. I think he started there in 1999. Is that right? And he's worked with the National Security Technology Department. He has specific interest in autonomous systems. We met about 9-10 years ago during a project he was working on that involved swarming technologies that took place at Aberdeen's, I think 7,000-foot runway at Phillips Army Airfield. And so he had a good setting for that application, did a lot of great work. He's also done a lot of work with DARPA that he's free to elaborate on. And he's also done some very interesting work for the railroads. And I hadn't even thought of some of the applications that he has in-depth experience in that milieu. So, without any further ado, Dave Scheidt, Dr. Dave Scheidt.
Thank you, Chuck. So, now how do we get to... Where's my mouse? There we go. Gotta find... Oh, there it is. That one. That one. Is that this one? Okay. So, for those of you who saw our talks yesterday, we talked yesterday about how the newly formed autonomous systems are changing requirements for communications. So today I want to flip that and talk about how intelligence methods, autonomous systems methods can impact communication systems and how they can change and potentially improve those. So I want to start with a thought experiment because to understand what an autonomous system can do for a communications network, you have to first start thinking about the information that you're going to transmit over your communication systems and what the purpose is that. So let me give you a thought exercise that I have a simple camera that's trying to examine what's going on in that street corner there on the right. And I have a simple network that's going to go point to point to an operator, and that is a fixed bandwidth, fixed latency. So if I have an ideal camera that I can dial up or dial down the amount of information provided by that camera, so how many pixels are provided, what's the optimum amount of pixels? How many pixels should I send over that network link to be able to try to improve the operator's understanding of what's going on in that corner? Okay? So, and it's a bit of a trick question because there's not a standard answer. So the naive approach is, well, all the pixels I can. I want to know everything possibly that I can get. But that's not really true. It depends on what you're going to use the information for and depends on what's going on in that corner. So if it is a dynamic world where things are changing, I may not want to send the maximum amount of information because with a fixed bandwidth, I'm going to incur some degree of latency. And if I'm trying to use this to manage that corner, to have a response and not forensically for intelligence uses where I can spend all the time in the world to sort out that information, then the timeliness is going to matter. Okay, so to further this thought, so imagine of some unit of time I can send one square packet, and over 2 units of time, after a couple of units, I will get back any one of those 3 pictures there. So I can send an initial snapshot of the right part of the screen and then a later snapshot of the left part or mix and match. And I get any of those 3 pictures. The top 2 don't even make any sense because I'm mixing and matching different amounts of temporal data. The last one makes sense, but it's old information. You see, there's no knowledge that the car's gotten around the corner. They're actually taken from these 3 pictures. And unfortunately, by the time I get any one of those, what's going to happen is the corner has nothing, the car's gone, given this amount of information. Another way to look at that is, this is overhead satellite imagery of a port, and that's actually, for anybody who's done intelligence, that's actually a submarine that's sitting at that port, and with a relatively low speed, fixed bandwidth, after 96 seconds, I can get a fairly good imagery in the upper left, and an intelligence analyst will be able to tell you, hey, I kind of know what class of submarine that is. Be extra credit if anybody could figure out what submarine that really actually is that we're looking at. Then I can get the information faster to the point where I can get some imagery in only 3 seconds, but that's almost useless. So again, so the question is, ideal amount of information to send, okay? And we have found that we can understand this mathematically through use of information theory, which many of you may know about. And the information theory is a way of measuring how much information in what's called Shannon bits, Claude Shannon back in the 50s came up with this, is provided by a message that you send over a computer network. And it is the probability that the message is true given all the possibilities and given what is known by the receiver. So, for example, if I told you, encoded up in ASCII, that tonight it's going to be dark, that takes 24 computer science bits, but that really gave you no information because everybody here in the audience knows that that's true. So I actually didn't provide any new information at all, but I told you it's going to snow. Well, it's really early to snow in the state of Maryland this time of year. It's possible, but highly unlikely. That's a highly unlikely event, and if that is true, that's actually a great deal of information due to the probability. So that's a lot of information there. So now let's think about a simple world for this. So I have an simple little building with 8 rooms in it, and there's a cat in that building. And what I want to do is I want to know where the cat is. Now the cat's alive, it can move. And if I have a sensor in each of those rooms that is a cat detecting sensor, that is a 3-bit question. There's 3 Shannon bits of what are called entropy initially because I don't have any sensors turned on. And I have no information, 0 bits of information, I have 3 bits of entropy. Now I turn on some cameras in 6 of the rooms, and I find there's no cat in 6 of the rooms, so he must be in 2 of the rooms. So there's 2 bits of possibility, 2 possibilities. So I have 1 bit of entropy left, and I have 2 bits of information I've gained. Now turn on all the cameras, there's my cat in room 1. Hey, I've got 3 bits of information, no bits of entry. But going back to the original question, how many pixels should I have? What if I want to know more about the cat? What if I want to know what direction the cat's facing? Well, that's 2 more bits if I'm using the cardinal points of information, east, west, north, south. 2 more bits to tell you that. If I want to know where every atom in the cat, I have an ideal sensor, I can tell you where every atom in the cat is. We actually weighed the average cat, calculated that. That's 10 to the 31 bits of information. I would be very impressed if anybody can give me a network that can give me 10 to the 31 bits of information before the cat is dead. Okay, so, and to make that even harder, if the cat's moving, and this is the key takeaway, if the cat's moving, at some point, if I try to use too many bits of information to describe the cat, that information is no longer true, and I've actually not gained information by the time it gets received. Okay? So, several key things that we use to try to understand the flow of information across networks. One is the information, the amount of knowledge we talk about systems. Complexity, this is how many possibilities there are. This can be difficult in military circumstances because it's open-ended. You say, well, how many targets are out there that I need to track today with my radar? That changes. That's not a fixed number. So the complexity of the situation is potentially dynamic and can grow and shrink. Entropy, that is basically an information theoretic representation of what I don't know, the uncertainty. A couple new concepts which are important in our recent discoveries is the notion of entropic drag. So you can think about that as the rate of change in entropy. So why is that important? So that is a way to represent the shelf life of my information. How long is it good? And I can use that to understand how much information I should even send. And then there's the notion of evolutionary entropy. This is the acceleration in entropy. Well, why is the acceleration in entropy interesting? That we can use to understand whether or not we should use learning or training techniques, including machine learning, because that's the rate at which information is changing. So if I can observe an adversary's training methods or their machine learning methods, I can predict how long it takes them to be able to understand my particular behaviors, understand what I'm communicating, understand what I'm sharing. I can defeat that by just changing the way I communicate, the way I work, and my behaviors more rapidly than they're learning. Okay. So some of the data, we use this to try to understand what I call the information paradox, which is some design criteria for networks. And that is these 3 basically statements. One is the more information I use to make a decision, the better that decision is going to be. And in general, that's going to be true. So if I'm assuming that the information I have is true, I would like to have more knowledge to help me make a decision. the longer it takes me to make a decision, if it's a dynamic world, if I've got an adversary that's actually trying to move and beat me as well, then the worse that decision is going to be. I need to, part of warfare is making rapid decisions, getting inside, what's called the opponent's OODA loop or decision loop. And the third is the more information I use, that takes longer to fuse, longer to communicate, then it'll take longer to make that decision. So that creates a paradox. Okay? And we find that the difficulty of a command and control problem, what I'm trying to solve, varies over time depending on the circumstance that my unit is in, and it relates to this unitless function there on the left. And I want to point out the graph on the right, which is a plot of how is the answer to that first question, of how many pixels I should use. So on the x-axis is the amount of information I'm sharing across that network. So on the far right is very little information. So it's a very low unit resolution, and I'm not sending much information across my network. On the far left is a lot of information. And the y-axis is how much uncertainty, how much entropy there is about going on in that street corner. So as you move from the far right, you have a first very granular, gross pixels, not a lot of data, it's hard to understand. And as you add more refined, higher fidelity information, that rapidly drops and you gain information and your uncertainty drops. But then you reach a point of diminishing returns, which is that local minima, and any attempt to try to use more information, communicate more information beyond that point actually causes you to have less knowledge at the point of actuation. So what we would like to do is be able to design communication systems to try to hit that minima. But because of that function there on the left, we know that actually changes. So we need to have autonomous systems that are going to adapt on the fly that will optimize the amount of information used to make command decisions for a military unit. So, some more data. We looked at different forms of communications structures. This is the topology that is used. So on the left, we have different forms of hierarchical structures, ranging from centralized, which is very simple, just two-part. We have a lot of leaf nodes and one centralized structure, and then regional coordination with just a few tiers. Local coordination, where we have a lot of information exchanged at the lower level and just a little bit of centralization, and then leaf nodes. And you look at that left plot, we're plotting on the x-axis the decay rate, how fast the entropic drag is in a system, how fast things are changing, okay? And on the y-axis is how much information we have depending on which topology we use. And what you could see is that for certain amounts of decay rate, different topological structures are the best one to use. So now that we can understand that, if we can now model and observe the current decay rate going on in the situation I'm trying to describe across my battle space, I can pick the right topology. Another way of looking at that exact same problem is on the upper right, and that's what's called a dominance plot. So each color represents a specific communications topology being the best performing one given all the topologies we looked at. And we're comparing that against two things. One is the situational complexity, how much stuff there is that we have to describe, how many targets are out there, how much is going on, what's the size of the packet were I to describe everything that's going on currently right now. And the other is the rate of change. How long, what's the shelf life of this information? How long is that information true? And you could see that there are a variety of different topologies that are the best for any one given circumstance. So that big red bar that you see on the bottom is a fully connected graph. Okay? Well, that makes a lot of sense because you have very low, essentially no rate of change. Everything is static. So if everything is static, I can take a long time to share information, make sure everybody's on the same page, coordinate decisions, because by the time I finish that, nothing will change. So I have the luxury of time. As things accelerate and get more complex, that breaks down, doesn't work. You move to what most networks are, which is a scale-free network, such as the internet. And that's that big magenta area. That works for a lot of situations. So internet-style topologies are good for many circumstances, but not always the best. As things start to grow in complexity and speed, you need to not use that, use other more decentralized approaches. all the way to the point where you start using gossip protocols, and eventually that large maroon area in the upper right is when communications does not work at all. You should just make local decisions, and actually having communications, trying to use them, will decrease your efficacy. So, what we're working on, we like to do in terms of trying to use autonomous systems techniques, is to use intelligent control to have the communications infrastructure, the network, become adaptive and reform itself as the circumstance it's trying to exchange information over varies. And this is important if it's a control network, which is different than a lot of the networks that you see. That's not what you're going to get in the internet network. So for a control network, timing matters just as much as the quality and the content of the information. So just like if I had a process control network like DeviceNet or Profibus, where I'm willing to drop packets in exchange for making sure that the really important stuff gets there in a timely fashion, a military network also needs to do that if it's being used for command and control. If it's being used for intelligence, general purpose information exchange, that's not necessarily true. So some of the things that we want to be able to change and have our autonomous systems adapt include the networking strategy, the routing protocols, the packet content, including whether I want to use security protocols. I have a very interesting story that I will not bore you with right now, but see me afterwards, you want to hear a story about the security protocols and how they can actually hurt your communications efficacy for military community controls and your information security countermeasures. So that's my brief thoughts on this, and I'll turn it back over to Chuck.
We have time for a couple of questions now, and if we keep up the pace that Dave made, we'll have enough time at the end to entertain more questions, which is our goal. Does anybody have any immediate questions?
Yes. Yeah, so let me repeat the question. That's an excellent question. So the question is, she knows that I had gossip protocols on there, and the question was whether there's times when we should use gossip protocols. And the answer is yes, gossip protocols are particularly useful. So, and I talked about this a little bit yesterday, but I'll go back over this point, that when you're building autonomous systems, and this could be an autonomous system where the human's actually the autonomous unit, so it could be a human making a decision, you want to have the same strategy for your communications infrastructure, your decision-making infrastructure, and your situ awareness infrastructure. So all three of those needs to map. So if you are using a swarming communications, or swarming control, like pheromonal ants and the like, then you need to mirror the communications with that, and that's essentially a gossip protocol with that. And the reason why gossip protocols and swarming control are effective is that they're highly robust and resilient. So there's no single point of failure. You can just communicate with whomever you can communicate with, and they're exceedingly rapid for propagating need and knowledge and coordination throughout a large network because there's not a lot of overhead associated with them. So the answer is yes, in certain circumstances, gossip protocols are very, very good, but they tend to be very complex, high-speed circumstances.
Okay, thank you very much, Dave. So our next speaker is Carl Murphy. Carl, when I met Carl 30 years ago, much major plus for my career. He started at NIST, worked there for several years, and then he and a colleague at NIST started robotic research as a small business. And since then, although Carl personally kind of maintains a low profile, he has a very big profile with his customers. He's done a lot of the groundwork for LiDAR development. Back in the 80s, we got a German Dornier LiDAR that was designed for wire detection. So it was far from ideal for a ground vehicle application looking for obstacles. But he gathered from that unit enough information to give us the specs on what we should go after when we build our first purpose-built LiDAR for ground robotics. So in any event, he's worked for the Navy, the Army, the Marine Corps, DHS, and a variety of other customers over the years, and has a wealth of knowledge on controls and then software development for networking, multiple systems, just a plethora of experience. So with no further ado, I'd like to introduce Carl Murphy.
All right, thank you, Chuck.
You're welcome.
It's already open. Which one you do?
This one. No, that's the title.
Not this one? Which one are you?
Murphy.
Murphy? Stop it. This one?
That one. Will those movies play on here?
It should, but
This is the only computer here that's not on the network. Everybody dumped their files for the projection upstairs hours ago, but because this isn't not on the network, it required some finagling with the system to get it to work. So that's what we're doing.
Depends on your level of trust.
Okay, good. We got that going. Again, thank you, Chuck, and thank you, MILCOM, for having me speak today. So Chuck asked me to talk about a program that we're working on with CERDEC up in Detroit on doing teleoperation with a high latency communication link. Just in case some of you may not know what teleoperation is, this is you have a robot, say, for example, a ground robot, and you're controlling it. And in this case, you have a human that's driving, and he has a joystick or a steering wheel, and he's saying, go forward, turn left, and go right. Those commands are sent across the data link to the robot, which then has some actuators on board that cause it to go forward and turn left and turn right, as well as sensors on board, such as a video camera that are taking images of the scene and then sending that information back to the operator, which is displayed on a computer screen or some type of screen. And then he looks at that and says, oh, there's a tree in front of me, I want to turn left. And so that's teleop. Okay, so there's a couple problems with this, with doing teleoperation. One is just understanding the scene that you're going in. Where is it safe to drive or not? The program we're working on is not really looking at that part of it, though there is some aspect of it. But there are different things of, for example, the round-trip delay for your control. And in this case, you have the OCU, or the operator control unit. That's the device that the guy's wiggling. That is read by a computer, sent over to a radio, sends it across the airwaves or some other communication link to to the robot. At that, they're received by the robot. It then determines what my actuation needs to be. I put more current into the motor. That then, the motor starts moving and the vehicle actually starts to move, which is our motion. The sensors on board are then seeing the scene and seeing stuff coming back. That information is then typically, if it's a video, it's compressed, then sent to a radio, back to the operator, uncompressed, and shipped to the screen that the person is seeing at. So this total delay on normal systems, you're at about 100 milliseconds or a tenth of a second. If you have a long latency radio link, such as a SATCOM, this can be in the order of seconds. And this is a very difficult problem. You say turn right on your controller, you still see the same screen. You're saying go right, it's still the same scene. And then 2 seconds later, you see the screen starting to move as the robot's turning right. Then you say stop turning, and it continues to turn for 2 more seconds after that. So the control delay becomes a problem for the operator. You can sort of adjust for that. If it's not too big of a delay, I'll turn and I know I'm kind of getting close, and I'll stop turning and I'll know it will continue to turn a little bit more. But if you have delay inconsistencies of sometimes it's a long delay, sometimes it's a short delay, this can happen on terrestrial links if you're doing a lot of hopping. Sometimes the radio is busy transmitting somebody else's data. But that delay consistency can also impact your ability to adjust for that as the driver. Also, you have problems such as dropped communication packages. If you tell it to go turn right 3 degrees, 3 degrees, 3 degrees, and one of those is dropped, it will only turn 6 degrees. And then even if all the comm and all the delays was perfect, you still have problems with the terrain and the interaction of the robot with the terrain. So if for example, on a skid steer robot, if you say turn 20 degrees, and a command that would send the same command over and over again, the robot would turn sometimes 20 degrees, sometimes it would turn 19 degrees, sometimes the same actuation. So the tracks are moving the same amount, but you'll get different performance on the car or on the vehicle. A classic example of this is when you're driving your car down the highway. You get on a nice straight road, you hold the wheel straight. Well, eventually it starts to weave off to the left or to the right. So you're always making small little adjustments. And so those sorts of things need to be taken care of. All right, so. No. This is the problem with delay. There we go. Okay, so to solve this, the system that we have for dealing with the high latency and some of those other problems is that we have we conceptualize 2 robots. We have the real robot, that's in this case, a Talon on the right side. It's a real robot in the real world. And we have this communication to it that's, a second, maybe 4-second round trip delay time. And then we have a virtual robot running in a virtual world. So when the operator says go forward, he drives the virtual robot. And because it's local, you have no latency. I mean, there's a little bit of latency, but it's down in this sub-tenth of a second type of latency. So basically, it responds right away. That, as he drives that robot through this virtual world, that path that the virtual robot is sent down to the real robot. And then the real robot attempts to follow that path. Then the sensor data from the real robot is sent back and arrives back at the OCU and gives the data that the virtual world or the virtual robot is using so that the operator can see where his virtual robot is in this world. So, for example, if the operator says turn 20 degrees, the robot will turn 20 degrees. The virtual robot does. That gets down to the real robot, and sometimes later it gets it and starts to turn. And it will say, I need to turn 20 degrees, and it turns that way if it's, say, the tracks are slipping somewhat, and it only turns 19. It knows it's only turned 19 and will continue running the tracks. If it, for some reason, overshoots and goes to 21, it will actually correct and turn back to the 20 degrees. Okay, so we ran this system. The screen you'll see is the display that the operator uses. In this case, so there's a couple ways of displaying where the virtual robot is. One is to build a model of the world, maybe using LiDAR data and 3-dimensional, painting it with the video imagery, and then moving through that just like in a video game where you would drive your first-person shooter, say, through the video world. Another way that we did was to actually show where the robot is in the scene. And in this case, if you notice the white square in the middle of the screen, that is not necessarily the robot, but the footprint or the shadow of the real robot. So the operator has driven that vehicle forward, and then if he lets go and stops, eventually he'll see the robot itself move forward and will eventually drive up and end up sitting on top of that white box. We ran this for demonstration. The OCU, or the Operator Control Unit, was in Detroit, Michigan. It sent out commands. We went through this extra delay box, so it actually just added more delay. That went to a Wi-Fi hotspot because they wouldn't let us plug into their network. Across the internet to the robotic research computers down in Gaithersburg, Maryland, just outside of DC, and then to the robot. So I'm going to see if we can run this movie here. Do you know how I can get that on there? It's playing on the screen here.
Usually you gotta click on the screen.
Let me move this over. Can I drag it?
Is in your presentation already? You might
No,
have to-
no, it's just a plain video.
Oh, if it's not in this presentation, it may not play it.
There it is.
There you go. Try to, you got volume?
No.
Oh.
Okay, so in this, it's starting out, the robot is just at the base of the screen so you can't actually see it. The white box is underneath the robot. So the robot is starting out on the right box. You'll notice that the person will, you can't see him push the joystick, but when he does, the white box will move forward. And then eventually he'll move it forward and stop moving it, let it sit there for a while, and then the robot will start to move. And so here he is pushing the simulated robot forward. The real robot is, from the video, still not moving. It then starts moving up. Before it actually catches up, the operator starts to move the simulated robot forward. If you can see, there's the red and green lines. They're where the robot would go if you went straight. They're sort of like the lines on your backup camera on your car. So in the upper left corner, it has a round trip delay of, it's 5.5 seconds. It's sort of fluctuating around, so it's a very, very high delay. If you're trying to actually teleoperate this without this, moving it forward, you would see nothing happen, let it go, and then it would just drive forward for 6 seconds. Also, one of the things is that if you notice the frequency of the communication, the frame rate is about 2 hertz, so we're getting about 2 pictures a second. And with that, there was this discussion earlier of, do you have more pixels or do you have higher frame rate? If you're doing normal teleoperation, you need a very high frame rate so that you can see motion, but that means that you're going to either have a higher data pipe or that you have less resolution, and so then it's hard to determine where it's safe or not to drive. All right. Now, if I can get my mouse over. There we go. Oh, I think that's... Oh, I don't need the last slide. So we've been doing that where there's more work that's going on for that. One is moving up to a bigger vehicle that's Ackerman steer. That's the normal type cars where the front wheels turn left and right. We're planning to run a vehicle in Australia from Detroit. We're also looking at using this for indirect driving. This is on the tankers when they're driving around, or some of the armored vehicles, they have to look through vision blocks, which cause structural difficulties to protect the inhabitants. So the idea is that you put a bunch of cameras on the outside and have the video inside, and we're thinking that we'll be able to drive those type of vehicles faster using this sort of system. You won't see so much of the vehicle going forward, but the left and right. And then the other method, we did a little bit of work on this, which is for, say, exploring inside of a tunnel network, where if you drive a bot in and it turns a corner, it loses comm, so you need to put radio links. That we'd have a string of robots that are doing leader-follower, so the first robot goes in, and then the following robots would follow behind it and automatically stop at these locations where the comms would drop out to allow for you to go through multiple hops and multiple bends inside of the tunnel network. All right, Chuck, that's
Okay, great.
good. Thank you. Oh, there's questions?
You have a question? Sure. You have a question? Okay, we'll
All right,
pick up
thank
at
you.
the end of the session. Thank you, Carl. Our next speaker is Dr. Ulrich Münz. He is a senior key expert in the power system collaboration for Siemens. He got his PhD through a joint program. His PhD was in automated control. It's in a joint program between the University of Stuttgart and the University of Madrid. I think that'd be interesting over a beer all by itself. And he has led a great deal of work in electrical engineering and telecommunications, both since about 2005. He has a specific interest in intelligent analysis of control design, and some of his work, as the title will indicate, involves microgrids. And I think he has the topic is very germane to things such as the vulnerability of power systems. About recently, who's the fellow that used to run Nightline? Remember? Well, anyhow. Who? Anybody know? Okay. Well, anyhow, a recent book has come out on the. That's it, Ted Koppel. Very interesting book on the power grid. So, with that, Ulrich.
Okay. Thanks, Chuck, and also thanks, David, for the introduction and for inviting me here to this panel. As Chuck already mentioned, my background is actually in control. I have also some background in communications, but it's a little bit longer time ago. I recently moved here to the US, to Princeton, where Siemens Cooperative Technology has also a research site, and I'm building up there a new research group for autonomous systems. And what I want to present here is an idea of autonomous microgrids, and I want to explain in the next few slides why autonomous microgrids is not just another term for smart grids, but it's really something else. It requires maybe for you to think a little bit out of the box, so it's not about communication issues, but more about what autonomous systems means in general and which challenges we are facing when we think of autonomous systems outside the classical thinking of autonomous vehicles and groups of vehicles. I will also point out a little bit some white spots from my point of view for current research in this field. I would like to start with two examples of joint research that Siemens has with different US military organizations. On the left-hand side is a funded project by the Office of Naval Research. It's actually colleagues of mine working together with David Scheidt on a multi-agent planning and scheduling to increase resiliency in ships. And there is this tabletop example that you saw on the lower side for the chill water system. And the other example that I have here is a battery storage system that Siemens built up together with the battery provider Vionics at Fort Devens to show how battery storage can actually supply or improve the power system quality if you have a lot of renewables in the systems. I've seen here at the exposition also smaller wind mills actually that can be used to supply islanded systems for communication. The kind of power systems we are looking into, or microgrids we're looking at, are usually a little bit larger. So it's tactical microgrids that could range from several hundreds of kV up to some megawatts actually range. So it's larger scale. Following up a little bit with what Siemens is doing in the area of autonomous systems, we see it, as I mentioned before, in a much broader range. So it's not autonomous vehicles, autonomous underwater vehicles, or autonomous planes, but we see it really as this next step for automation systems. So coming from automation systems in industry, energy, and transportation, which have been developed over the last more than 100 years, we believe that autonomous systems will revolutionize the way how we see automation systems in the future. There are three main areas where we are working on at Siemens, which is autonomous production systems, autonomous energy systems, and autonomous transportation systems. The pictures that you see here are just some examples where we have been working on recently with my colleagues at Siemens Corporate Technology. And I will just pick one example here for autonomous energy systems. Thinking about autonomous systems, there are two key components that I think that have been satisfied from our perspective to say that it's really an autonomous system, and it has to, of course, solve a high-level task without human interaction or with limited human interaction, as we've seen in the previous talk. So basically, the human operator just gives some commands, and the robot or the system should automatically figure out how to solve this. And you also don't want to have a detailed programming. So it's not that you basically program hundreds or thousands of different options and it just chooses one, but it really should be intelligent enough to come up with a solution by itself. Now, if we transfer this to microgrids, the vision that we have for an autonomous microgrid is that on the one hand, you don't need a human operator of the microgrid. So basically, you have something like a microgrid manager, which decides at which point of time you're turning on diesel generators, when you can turn them off, when you have sufficiently renewable generation, when you need battery storage, or when you can use storage as a load to charge them or discharge them. So this is called economic dispatch usually. But there's another tricky problem that you have to consider, and it's again going in the same direction as we've seen before in David's presentation. So you have different agents, you can call them, different generators, and somehow you have to come up with a decision on a joint frequency, which is the frequency we're running the system at, which is the voltage we're running the system at. Of course, a lot of tradition, how we have done this in the past, and we have to stick to this, at least from an industry point of view, because we want to use existing hardware. But still, the mechanisms underlying this way of synchronizing frequency and voltage are a very interesting topic of ongoing research. If you now go to the right-hand side, and it comes to the question of how can we set up a system that does not require detailed engineering and detailed commissioning, which is usually quite expensive and time-consuming. This is even a more interesting field. So you want a system basically where just take the components, plug them together, and somehow they set up by themselves. They figure out how to parameterize this microgrid manager and also how to parameterize the local controllers of the different subsystems. And what happens, or what you would like to have actually, is what you see on the lower right side is basically if you just plug them together, if you do it as it's usually done today during the commissioning phase, then you see a lot of oscillations, and you really do a manual tuning in order to get to a system that looks like at the right-hand side that has a performance where you say, okay, frequency is not oscillating after load step. We don't have power oscillations between the generators. That's actually what we would like to have. And the question is, how can we get there and what is needed to get there? And actually, I came over giving this presentation here in this session because we had a discussion in June with colleagues from CERDEC about exactly this problem. So when you build up a technical microgrid somewhere out there, they had a strong interest of using renewables because they're just cheaper to produce energy. But then they're coming up with the question, okay, do we need a specialist on site? Do we need to do all this engineering on site? Or can we come up with a solution that is basically self-parameterizing in some sense? And this gives somehow, of course, a very personal view on how the research landscape looks like and where we are there actually today. So if you look at the left column of conventional generation, means a lot of maybe gas turbines or diesel generators, classical generation for the power system, then we would say that the autonomous operation or the operation of the system without a human operator, this is basically something state of the art. It has been done since probably 50 years. When it comes to the feature of plug and produce, which you see in the lower two lines, this is something which today actually is done manually. So you don't have a system that automatically parameterizes itself. Usually you have supporting tools that does this. The key challenge comes into play when you say, okay, we want to have more renewables in these systems. Why? Because it's usually cheaper. In particular, if you think you have some really far out location, so all the petrol that you're burning in the diesel generators, you just have to bring them there. In particular, if it's in a combat zone, it's even dangerous to take the tank truck getting the fuel to your site. Right? So renewables are really a payoff here. And this is an active field of research, as you surely know. If it comes to economic dispatch, so who is providing the power at which point of the time, how you can balance the power between the different generators. That's something which is regularly done today in research projects. You have some products also for companies that you can buy, and there's a whole bunch of field tests for this system. However, when it comes to the question, how can we actually coordinate the different systems, the different generators, so that we can avoid power oscillations and frequency oscillations between them? This is something where I think that still a lot of research needs to be done, in particular if you're looking into off-grid applications, so not grid-connected problems. And now turning to the lower right corner, when we say, okay, we want to have a lot of renewables because it's cheap, and we want to have it building up by itself, so plug and produce. This is something where I would say hardly practical research has been done, practical in the sense of that it can really be applied in practical system, and we don't see field tests in this area. So I think that's really a huge wide area of research that should be addressed. No, actually we are looking very much into practical problems where we say we have to use existing structures, existing components, and the common components today are not really able to have a fast real-time communication. We have communication between the manager and the distributed generators, but in particular for the part when you say you want to have power stability, basically, this has to be done in a completely decentralized fashion. That's state of the art today, actually. I mean, we are looking into more advanced topics, but if you want to deliver something in the next 3-5 years, that's probably not the case. Very good question. Sorry? Yeah. So just one last point to show here. This is one piece of the puzzle towards autonomous microgrids that we developed here at Siemens. And it exactly addresses the question, how can we tune the controllers in such a microgrid so that we avoid these oscillations? What we developed here was a closed-loop optimization algorithm that basically takes the model of the system that you have, tunes the parameters of the different controllers, and exactly comes up with a solution that you see on the lower right-hand side. This is here a simulation. We are right now working on field tests and tests actually on one of the customer projects on one of the Galapagos Islands to really prove that this algorithm can shows the same performance not only in simulations but really in practical systems. And with this, I would like to come to the last slide just to summarize. So autonomous systems, autonomous microgrids is not the same as smart grids, but it has the feature of plug and produce. And this is, from my point of view, a feature that requires a lot of attention in the future for future research. I showed you one example briefly where we have done this in Siemens. And the main open challenges, as I just mentioned, are really this plug and produce, how you can build up a system without doing detailed engineering. This can easily take weeks or months if you do this manually. And the key benefits, just to finalize, of course, as I mentioned before, reducing costs of energy generation and increased availability of the system, because it's resilient. If some parts drop out, you can just automatically redesign the system, the control system, and everything works fine again. Okay, thank you very much.
Okay, our next speaker is Brian Sadler from ARL. Brian obtained his doctorate from University of Virginia, and he's a specialist. Well, first of all, he's a ST, which is a level above the normal GS scale, both in management and remuneration. So he's a very well, you take what you can get, right? so he is a major league leader at ARL for their very rapidly growing and diverse research projects in this area. He's also won Outstanding Inventor of the Year, and I noticed in his bio that he's published over 350 technical papers. So a very productive career. This is far from over. And I find
says you.
Yeah, that's right. That's right. I'll vouch for it. So he's primarily focused on networking, intelligence, and a whole plethora of other technology areas. I'd like to point out generally that although the schedule may say that we're quitting at 3:15, there is no one in this room at the rest of the afternoon. So we're going to run till at least 3:30 and then move to the general discussion area. Thanks.
Okay, so I'll try not to go till 3:30. Thanks, Chuck. Chuck and I go back a long way. It's an exciting time for autonomy. You know, and there's a heck of a lot going on, and there's a lot going on in networks too. I'm going to talk about the confluence of autonomy and networking in the Army context. And I'm particularly focused on tactical networking. So to me, the Army has a tough nut in terms of tactical operations in nasty environments. We've always had a tough networking problem. The mobile ad hoc networking problem has been a conundrum for us for decades. But now with the advent of autonomy, and I think with the advent of a lot of interesting cognitive technology in the radio space, we are progressing to an interesting new frontier. So I'm a research guy, and I'm going to talk about research issues across both of these spaces and then think about the combination as we go forward. So I'm going to be very sort of forward-leaning in what I'm going to talk about. You know, if you're around the autonomy space these days, you've heard of the third offset strategy, and I think it's probably fair to say that most of the thinking in this space is big air, big Navy type, with perhaps less in the Army tactical space. One of the reasons for this is because it's a lot easier to do things in three-dimensional open air than it is to do it in a tough tactical environment. So, but this is the kind of places we want to work. We want to work in megacities, and looking out not too distant future, you know, the predictions are that that's where we will be operating to a large extent because those will be the population centers. Okay, so a few comments about autonomy. Then I'm going to do the same thing for tactical networking, and then I'll have a chart on the combination of the two, okay? So I've got 3 more charts. So where are we in tactical autonomy? Going back about 10 years, we had a hard time taking a single small robot and navigating it in an environment like this, making a map during the SLAM problem, having it have sufficient onboard processing to do ranging, to do imaging, to do the sensor fusion we needed to do. Over the last 10 years, that's changed quite a bit. We can now do this on small platforms, quad rotors. We can bring a quad rotor into this space, map it entirely autonomously. We can do it collaboratively with multiple air and ground units. And we're getting better and faster at this. So it's not too far. We're not too far away from swarms. Swarms used to be really about flocking behavior. Now we're talking about coordinated groups. We can do this outdoors now, and it won't be too much longer. From a research perspective, we'll be able to do swarms in an environment like this and go pretty fast. For the Army, we have to think about a heterogeneous mix. And this is a mix across ground and air, across small and large platforms, and teaming with men. The reality is that these small platforms, like a quad rotor which hovers, and you've all seen all the videos, you know, hovering is the least efficient form of flight. It just sucks your battery dry in a very short period of time. As I like to say, there's no Moore's law for batteries. We're getting a lot better at the processing, the convergence that we see into small devices, but the battery, the rate of increase in the battery is slow, linear increase. They're getting better for sure. We also need different kinds of batteries, so this is a significant problem. So a small quad rotor that can operate in this environment, 10 minutes, 20-minute kind of lifetime. Thinking larger tactical, then, we have to think about a mix of platforms, large and small, and we have to do things collaboratively. We're forced into the collaborative space if we want to do some kind of larger scale operation because of this capabilities and lifetime as we go from small to large. We're talking about highly distributed. I guess that's pretty obvious. We want to operate in and around buildings, underground, and so on. And we like to do this at a larger scale. I mean, right now we're talking about one guy or several guys, one agent, one teleopt agent. We'd like to flip that around, and we'd like to project autonomy out in front of us, for example, into a building. I think it'd be great if we could get away from the kick the door down and a guy goes in. The way we did it in World War II, And we're still doing that to a large extent. In the autonomy space, we're really starting to push on op-tempo now. Because op-tempo, we're pretty good at rolling around in office buildings. We're good at that. And you're going to see a lot of commercial things that do just that, roll around in a space like this slowly, and they'll have a lot of smarts on them. For our problems, we want to go really fast. We might want to crash a few, right? But we need to go somewhere and we need to go quickly. We want to project this ahead of ourselves. Then we need to go fast, and we're pushing on op-tempo. And another key assumption is that we're going to have a network. I'm not going to do collaborative autonomy without a network. I'm not going to go into some kind of fully autonomous operation. I'm not going to step from teleop to fully autonomous. In fact, we don't even have a good terminology. We do not have a good scientific terminology for what's in between teleop and fully autonomous. Autonomous means that the agent can do something by itself for some period of time. It should be my teammate, however, and that's how we think of it. We think of it as assisting technology, and that means there's got to be an interaction. So I'm arguing for collaboration. I'm going to have a network. From the autonomy side, we like to assume we've been handed the network. Along with that, we're going to have access to knowledge sources. We'll have knowledge bases. We'll have tactical computing. I need a variety of computational abilities. Some of that I may have to bring along with me in larger vehicles. Okay, so that's some comments on convergence of technologies and autonomy for the tactical space. So now let's think about ad hoc networking. So you're at MILCOM, you've probably heard of all these technologies. I mean, we're becoming more cognitive. We're adding more computation into the radio. It's not a push-to-talk device anymore, right? We want to assess the environment. We want to know what's out there, what's not. We need to be much more intelligent about how we manage our spectrum. Another direction we're going is diversity in the sense of having multiple radios. So your cell phone has at least 3 radios in it, right? It's got microwave, it's got Wi-Fi, it's got Bluetooth. It might have multiple cell standards. Your cellular device has multiple radios in it. And we need to think the same way in the Army space, largely because of, well, for several reasons. One is just penetration. Cellular's not so great when you get into the basement. It's because of the penetration. Microwave does not penetrate particularly well, whereas other lower wavelengths will penetrate better. We also have to think about optical and so on. There's a lot of pieces to the puzzle. So we really need to think in terms of that. And I didn't mention the EW problem, the determined adversary problem. We want to do dynamic spectrum access. We'd like to monitor the spectrum, adapt, and so on. Along with that cognition comes positioning and tracking, because if you have an ad hoc collection of agents, things like power control become really tricky, right? It's not a centralized infrastructure-based thinking which goes into ad hoc. Consequently, you can't play a lot of the central management games that commercial plays. So it's definitely behooves us to know where our nodes are. We want to know where our humans are. A part of the whole networking infrastructure is the positioning and tracking in these difficult environments. Other speakers have mentioned relay and so on. And the ability to interact with computation. So if I'm going to manage the network, it's the same kind of thinking that it goes into managing the cognitive collaboration. I need access to computation. Okay. So, last chart. So, I make the following claim. You can't do collaborative autonomy without a network. And I believe that we should not do ad hoc networking without autonomy. I think that autonomy brings to the table the ability to do a leap ahead in the ad hoc networking space that we've been waiting for some many years. So, if I were only going to pick one bullet on this chart, it would be the first one, autonomous mobile infrastructure. The thing that makes commercial so great is that it's all wired. The cellular system is a massive amount of wires that flows over the entire Earth. And we sprout antennas off those wires. and you walk around near an antenna. So you're one hop into the wire. That's the goal of a commercial process. We do not have that in the ad hoc setting. But what we can do is bring our own mobile infrastructure. So we can bring base stations, or whatever label we want to put on them, mobile access points. And introducing these into our systems, making them responsive and adaptive, in my mind, is the solution, or a solution, a way forward to all of the challenges, or many of the challenges we've had with mobile ad hoc networking. I personally believe that the sooner we accept that fact, the better off we are. We can do things like maneuver for topology, right? If I can introduce autonomous agents, I can autonomously maneuver them such that our networking is enhanced. I can do things like find sources. I can find the bad sources. I can find guys who've wandered out of my network and so on. And I can do other things like data mules. I can move massive amounts of data around physically. And the robotics guys have spent a huge amount of effort in the last 10 years solving the geolocation problem for us. The robot is expected to be introduced into a completely unknown three-dimensional environment, wander around and explore, make a map, and figure out where it is in the map. And that's precisely the problem that we want to solve in the ad hoc networking. So I think the conjunction of these technologies offers us a huge potential interesting advantage. And so these are my thoughts on where these trends are, where these research trends are, and I think where they can potentially get us looking out a decade or more. Thank you.
Great, Brian. So I suggest we hold, since we're really close to the end, we hold the questions until the next speaker finishes. Is that okay with you?
Sure.
Okay. So our next speaker, and thank you, Brian, is Dr. Mudhakar Srivatsa. He comes to us from IBM up in New York. He's been with IBM for 10 years. He's a master inventor up at IBM. And he has done a lot of work on cognitive analysis of spatial and temporal data, which is a very powerful tool in the world of autonomous systems. He works at the Thomas J. Watson Research Center as a principal research staff member there. And I think that pretty much wraps it up. He has a very broad perspective in these areas. So,
thanks, Chuck.
Thank you.
All right, so I'm going to be sharing some thoughts on cognitive vehicles and where things have grown in the last 5 years and what are the challenges we are expecting to face in the next 5 years. And I'll also cover some of the deployments that we have done in over 1 million vehicles in Europe, 500,000 vehicles in the US, and some in Africa. So this is where we are today. I mean, we do have a large number of connected vehicles that are hooked up to the internet one way or the other. And a lot of them have a large volume of code and data that is residing inside them. And large volume of data comes from various sensors like LiDAR and visual imaging sensors and your OBD2 onboard diagnostic sensors that are there inside the vehicle. And very soon, or even as it stands now, connected vehicles today probably contribute to the second largest data generator in all that we see in Internet of Things. So what do we get from systems like this? What we get from systems like this is hundreds of sensors that are connected, and we get data from these sensors at nearly a frequency of 1 hertz, so 1 sample a second. We get a wide variety of inputs ranging from just location, time. You have information on windshield wiper status being on and off, external temperature, light, gear selection, whether your stability control system indicated slipping of the wheel, advanced braking systems, lane detection. So you have about 40, 50 to 100 different attributes that's being sensed roughly at 1 per second. And this data needs to be analyzed in real time, and you need to be able to produce actions out of this data in real time. For instance, you might go on black ice, your wheels slip. There is perhaps very little you could do for your own vehicle, but certainly vehicles that are coming behind me in the same direction could be notified, and their stability control system could adjust and adapt to the fact that they are potentially going to go over slippery ice in the next few milliseconds or next few seconds. So we have a wide range of applications here, ranging from safety, like distracted driving. So a lot of cars have cameras facing inboard, especially for teenage drivers. These are wide-angle 120-degree cameras facing inward, facing the driver, and they're doing various sorts of activity detection. Am I still paying attention to the road? Am I texting? Am I drinking coffee? A whole bunch of activities are detected in real time, and potentially the driver is alerted to take corrective action. There are other applications ranging from automatic crash assistance, remote vehicle diagnostics, various location-based services. But what I'll do briefly is to talk about my personal journey in this space, which started maybe about 10 years ago, and where this chart basically covers where things have been T-5 years to now. In this last 5 years, I've personally led the deployment of a system of this kind over 1.2 million vehicles in Europe, and several installations of this size, a couple of millions of vehicles, where we are collecting data in real time, sampling about 50 to 100 different attributes from each vehicle at a sampling rate of 1 Hertz. So what we have learned in the past with deployments of this size, I'm going to talk about 2 areas, the communication and the information. What we have fixed in the last 5 years is basically a whole bunch of problems in comms, primarily aided due to advances in various technologies. So T-5 to T, what we have done is basically we have lightweight messaging protocols that are several orders faster and yet secure in comparison with, say, protocols like HTTPS, with very low networking overhead, with very little battery consumption. And the key here was being open with these protocols, meaning this is an open, publicly available protocol using which any participant, any sensor can publish data using this protocol. But the key here was that it was optimized for messaging, meaning unlike a TCP-based protocol, which is meant for transmitting large volumes of data, these protocols were optimized on sending large bursts of large data, but bursts at unpredictable times. There were issues with maintaining persistent connectivity because these objects or this million vehicles are moving around, and we now have hardware-based solutions that can maintain millions of persistent connections, can send 13 million messages per second in a non-persistent mode, several hundreds of thousands of messages per second with full reliability, and so on. We have exploited things like white space networks, unused spectrum, especially for cellular networks that transition from 2G, 3G to LTE. It has freed up a whole lot of control bandwidth that's now unused. This bandwidth is small, maybe 5, 10, 20 kilobits per second, but all that unused bandwidth could be used potentially in transmitting sense data from these vehicles. So this is what we have achieved in the last almost 5 years, where we have been able to deploy systems in production, working over millions of vehicles, collecting data in real time, processing this data, and delivering the results of this back to the vehicle. To give you one simple example, this was an instance where it was the problem setting was that of urban planning in Nairobi, Kenya. And what we did was to instrument garbage trucks, and you might be surprised why garbage trucks, because we needed vehicles that have a full coverage of road network, meaning they go on every single road in the city every so often. And we needed vehicles that government has some control over, meaning they can go ahead and instrument all these vehicles. And this was done about 18 months ago, and it was a year-long exercise, 18 months to last 6 months ago. And the estimated savings from such a deployment was estimated to be about $600,000 per day. A sort of a byproduct that nobody expected was that 1,200 metric tons of garbage was collected more than the usual. And this was completely unexpected byproduct. It's just because the vehicles are now have embedded sensors in it. The drivers were not lazy, or the drivers were not deviating from the paths that they were supposed to take. They kept on track, and they ended up collecting 1,200 more metric tons per day of garbage, which resulted in additional problems because their garbage disposal system now had a much heavier load than what they were used to. But nonetheless, that was an unexpected byproduct that we didn't anticipate when we went ahead and deployed this solution. There is actually a very interesting TED talk on this topic, and I'll leave it for offline viewing. So where we are now and to now plus 5 years. So in this journey, as we continue, these are the problems that we are facing today. We have been looking very extensively into distracted driving as an application. It's one of the leading causes of death other than medical reasons, like a cardiac arrest. What we have now is systems with a wide angle 120-degree camera facing both inward and outward. We collect data from the camera, from LiDAR and OBD2. OBD2 is onboard diagnostic sensors from all cars. It is standard in all cars manufactured after 1996. This results in about half a terabyte of data per day per vehicle. So it's a large volume of data. If you operate the vehicle full day, you get about half a terabyte a day. Of course, normal users may not operate the vehicle for all 24 hours a day. Commercial users may operate the vehicle for about 12 to 16 hours a day, so you will still expect to generate maybe about 0.1, 0.2 terabytes of data per day per vehicle from a system like this. Part of the problem has been alleviated in terms of computational challenges through embedded GPUs, graphics processing units, and FPGAs, but they don't fully remove the problem. The bigger problem that we are seeing here is adversarial learning, which are in the form of data injection and poisoning attacks, induced targeted misclassifications. I'm going to give you examples in the next chart. And the more infamous I don't know problems, a lot of these deep learning based solutions like convolutional neural network often try to force a classification. They are not good at admitting that I don't know what class this image belongs to. I'll again give you examples in the next slide. And being very robust under different environmental conditions like fog and snow and rain and so on. So these are the sort of categories that we are interested in. We have a large bunch of states we want to detect when it comes to distracted driving. Some of them are stateless, meaning I can detect on a snapshot of an image. Some of them are stateful, meaning I need to understand the temporal sequencing of images and only then I can detect a particular state. Here is the challenge that I was referring to, adversarial learning based challenges. So in this particular example, I have an image on the left. It looks like a panda. It is a panda. The network concludes it's a panda with 57% confidence. I add a very targeted noise. As you can see, the noise is very small, 0.007 times that seemingly random black and white image. The resulting image is shown on the right, which also looks like a panda, but the classifier thinks it's a gibbon with 99% confidence. So there are very subtle and very interesting ways, because once we understand the inner workings of a neural network, we know it is based on stochastic gradient descent. We know which are the dominant vectors that determine classification into a panda versus a gibbon. So you can basically confuse the classifier with very, very little noise and let it believe that it's actually a gibbon with very high confidence, when in fact it is fairly close to a panda. The problem gets even worse because a neural network is often not good at admitting that I don't know what it is. So these are real examples, and the classifications are written in English below. That random looking black and white image is concluded as a robin in the first case, cheetah in the second case, armadillo in the third case, and a panda in the fourth case. And similarly, all the other images, like the next line is centipede, peacock, jackfruit, bubble. The next line is penguin, starfish, baseball, a guitar. And the last line is a freight car, remote control, peacock, and African grey. So it's very easy to introduce misclassifications because the network is ultimately a real valued function that goes from the image to a class. And it does not admit that I don't know what this particular image is. Instead, it tries to compute the real valued function and tries to determine the most likely class, which in some cases can be totally wrong. In several cases, the confidence is not very reliable. Like in the example, what looks like a 4 has a lower confidence than a 6. Like 4 had a 80% confidence, 6 has a 90% confidence. Very often you start seeing confidence inversion that happens between the true label and the predicted label. So these are all some of the challenges that we are seeing, and why these things are a challenge is because think of this as a stop sign, and there is a graffiti on a stop sign that induces a misclassification, so a stop sign no longer looks like a stop sign, and we have a cognitive vehicle that's driving through. It no longer recognizes the stop sign, and it can cause a whole lot of havoc, and all that I may need to do is to do something like this, change maybe less than 0.7% of the image in order to do so. So these are some of the challenges that we are dealing with going forward in this journey. So with that, I'll stop.
Yes. So first, do we have any questions for either Dr. Sadler or Dr. Srivastava? Any questions for those gentlemen? And after that, we'd open up to anyone on the panel. If you have any questions, now's the time. Okay. Well, yes, there's a question. Okay. Come on up.
So I'm not sure actually who this question should be addressed to, so it's kind of general and it's kind of coming from my own experience and research. It's in the context of control and communications. In general, my experience is that communications, as we know...
Wait a minute. She'll be quiet in a minute. Okay. Okay. I couldn't hear any of that myself. So.
Sure. So my question is general in the context of communications and control and autonomous systems. Is my experience is that in general the communications is designed for kind of old kind of systems, internet-oriented systems, large packets, a lot of overhead, whereas probably large latencies, right? So I'd like to sort of see a comment on the notion of a lot of times in controls what we really need is a very, very reliable, very, very short packet at very low latency. And infrastructure for that is, to me, I've seen very little research on that topic, and I feel that's maybe I'm missing something. Maybe you'll tell me that's something well developed. I'd like to sort of see that pursued.
Who wants to address that?
Multiple ones might have DevTech developed.
Okay.
I'll start with. So let me first start with looking at autonomous systems that are cooperative autonomous systems, including talking to a human or other autonomous systems. One of the things that an autonomous system gives you is the ability to make decisions when you do have difficult communications. So a way that in the autonomous systems I've designed, we try to look at it, is look at communications opportunistically. So the existence of new information for your autonomous system can help improve performance, but one of the fundamental reasons why you use autonomy at all is to provide robustness and resilience for when you do not have communications and to be able to continue to carry on the mission. So that's one thought. The other thought is when we're designing an autonomous robot inside the robot, where we're not looking at communicating to other actors, to the operator, we often use multiple buses, multiple internal communications buses that work at different speeds. So you may have a very high speed bus that's controlling your, for UAV, for example, that you're controlling, the autopilot is controlling for stable level flight, but you'll have different buses for, and different communications mechanisms for the internal components that are working at more leisurely rates for your machine learning or for your more deliberative control. And that's buses, high speed will be 50 millisecond bus rate, and lower speed will be, we're going to say 1 hertz for making more reactive decisions.
Just another comment. That's a great question, Friedrich. I think if you're doing this wirelessly, you better be redundant if you really care about that latency, right? Especially if you have a determined adversary, right? Another comment is, in the history of control theory, we don't model delay and time-varying delay very well. We simply lack the mathematical constructs to even handle these problems. This is still an open mathematical question. Getting your hands around this is not trivial. What do? We over-engineer, right? And one way to over-engineer is add a lot of diversity. And this also points to the notion in control that if you know you're going to have a lot of time-varying lag, then what do you do in your autonomy? It has to be able to deal with that. Right? That's the other side of that question. And it's still an active research area, I'd say.
Going back to the comment earlier about having multiple antennas, so nowadays this notion of multipath communication has become very popular. In fact, in your iPhone, it lets you do multipath communication on both Wi-Fi and cellular at the same time. So your same TCP connection, parts of the packets can go through your Wi-Fi network. Part of them can
Could
go
you
to
bring the mic up a little closer?
Part
That's
of them can go through the cellular network, for instance. And if, say, the Wi-Fi network gets jammed, automatically the multipath TCP protocol starts pushing more packets to the cellular network and so on. This goes back to the point of over-engineering, or maybe just enough engineering, wherein you build in the system with multipath as your transport protocol, and based on the time varying conditions of each of those separate channels, you can decide to send as many packets as you want on one channel versus the other.
great.
And maybe
That answer your, another one? Sure.
just one point to add from an industry perspective, for the customers that we at Siemens usually work with. When it comes to communication, and you use communication to improve performance, as David basically said before, then that's of course a good thing. So you can suggest to use more communication, and if then something goes wrong on the communication side, you're losing somehow performance. When it comes, however, to safety or critical stuff, that you say, okay, I want my protection system to work under any circumstances, then it's really challenging to convince end customers to use communication-based protection systems, or basically a protection system that only works if the communication system is running. Basically because they're just afraid that if the communication is not working for whatever reason, then they're losing their protection. I would not say I don't trust it, but the customers don't trust it. I mean, I'm talking about industrial customers, large entities, and so on.
Thank you.
Hello, my name is Mike Piasecki, and I'm president of Dragonfly Pictures. We
Could you get up a little closer or pull the mic up toward you?
recently won a phase 2.5 SBIR for doing something pretty simple, which is to put two antennae onto a multi-copter UAV. Why would we do that? But the littoral combat ship has difficulty overcoming line-of-sight issues with its mine countermeasures boat. We elevate with a tether, a powered tether, a multi-rotor, and transmit and receive on that platform through a fiber optic tether down to the ship, and up through the tether to the robotic boat. I was wondering, do you see any applications on a ground-based scenario that would also, that one of the unique features of it is that it's designed to move. It manages the tether tension, and so it's designed for a mobile application as well as stationary. Do you see that as sort of a new paradigm for platforms assisting in some of the line-of-sight issues for comms?
So, in the Army perspective, I mean, one of the things you think naturally about is having a tethered autonomy above you. But then operationally, you run into issues when you're moving around in a complex environment, like trees and power lines, and et cetera. So this is good news, bad news. Now, if you're in a fixed position and you want to tether something, that's appealing, because of the power issue. If I can put a quad rotor, a few hundred feet above me and sit it there for hours, that's very appealing. It's small, and it's, and you can power through the tether. So I think that the answer is yes and no from an Army perspective. To do it on the move is, challenging.
And again, it's terrain dependent. If you're out in areas where you don't have the tree covers, you don't have the antennas, you're not in urban, it definitely could be doable. Of course, in those environments, you tend to have better. I mean, if you're going over the horizon type distances, then that could be helpful.
So a few years ago, DARPA had a program called Landroids, where they had little ground robots that would work inside of buildings to establish an ad hoc manet for soldiers to work in urban canyons, in underground facilities, and the like. You could think of extending that concept by using quadrotors, things that could fly, that could more rapidly maneuver, and actually go up vertically, which the Landroid robots could not do. Particularly if, so there's a Professor Nicholas Roy at MIT had showed that they had the ability to fly at speed in underground parking garage, avoiding cars, avoiding the pillars in the parking garage. So you have that sort of mobility, that sort of obstacle avoidance capability, combined with the sort of capability you're talking about, could be a more advanced version of Landroids, I would think.
Yeah, and I'd point out that we actually looked at that very closely as part of a 2-year program that we demoed, and it wasn't your system. I'm a little bit familiar with your system, but the group that our folks picked to do a demo for us had the unfortunate tendency to crash several times, right? But that didn't damp the interest in the area. There are lots of first of all, because of the expanded payload that you can put up, there are lots of folks who don't require lots of mobility of the platform that you're tethered to. There are lots of people who are very interested in using existing mission packages to extend the capabilities greatly. Electronic warfare is an example. If you can get up 100, 200 feet, it makes a huge difference in the productivity of a lot of the existing equipment we have. So I think it's as Brian said, it's a winner in the right application, and if the reliability is there.
Right? I mean, if you've got the tether and you can use it when you can, you should use it. Right? Why not? Right? But if you can go untethered, or if the tether breaks and you still have an autonomous platform, that's also good. So to me, the combination could be very, very powerful.
Yeah.
There are people looking at wireless energy transfer. Like if I put a laser on the quad and it's got a solar cell and I'm recharging that way, but it's complicated, power hungry, not safe.
Right.
People have demonstrated this also.
Yeah, that was one of the phase one. That is one of the options.
Yeah.
He's saying phase one has that as one of the options. Any final questions?
Quick question, John Matias from Air Force Research Lab. Just wondering if you could comment on compute architecture. So if you look at like neuromorphic computing, IBM True North chip came out of DARPA Synapse to enable stigmergic coordination, for example, very low power consumption in terms of the processing to help with the battery aspects. If you can please comment on that and the future of that intersection.
Yeah, so, we're going to see a small tidal wave of devices, as you're pointing out. These are coming rapidly, and there's clearly things you can do with these new computing architectures, which are very appealing. Although, as Shoemaker showed, there's issues, but nevertheless, they bring a lot of new capabilities. So we're going to see this. So the question is, from an architecture perspective, we don't know what wins or how. I think we're just getting our feet in the water as far as, are we going to use them? Yes. Are roboticists going to take them and strap them and put them on their platforms and try everything you can imagine? Yes. I think that's healthy. But I don't think we know what's the winning architecture. And in fact, to me, it's not about one architecture. It's going to be modularity. It's about embedding. It's about repurposing. It's about, right? Because so far we have this, we sort of have this mentality of it, that we have a neural net. No, I'm going to give you 10, 20 of different kinds for different purposes. You're going to embed them in your control. You're going to use them for perception. So it's pretty exciting. It'll be interesting to see how it sorts out. But they're going to be in cell phones. Right, clear.
So there's been a big push in this whole non-Neumann architectures for computing, and part of it is the synapse chip sort of an idea where you burn an entire trained neural network into a chip, and then you can use that for prediction at maybe 1/100th the power consumption as that of a normal computer. These things have shown some success, but the key here, as Brian pointed out, is about how agile they are. I mean, if I have to change the neural network, the way it is designed is that the neural network is burnt into it. So changing there is no notion of changing a portion of it. You have to reburn the whole new neural network once you have it. But people are working on it. I mean, we are looking into techniques wherein a small portion of the network could be changed. Maybe you only want to change the convolutional filters in your network, but not your classifiers. So things like that are being looked into. But the more agile they become and more programmable they become, that's where the real success is.
I think, and we've looked at actually hybrid architectures. So the spiky chips and the new neural convolutional neural networks are some of the best general purpose reasoning systems that we have. But we look at it for the problem domain that Ulrich and I look at, which is fault management of electrical systems. So I kind of get Ohm's law. Right, and I don't have to train something by frying 50,000 circuits to say, oh, look, I have a short. So some parts of that, traditional architectures, I think, are better at. So how can I create, and what we're investigating is, how can I create a hybrid architecture that takes advantage of the general purpose contextual reasoning of, I really don't know how to model this, can I learn what's going on, versus stuff that, yeah, I model this really well, and I don't need, I already knew how to do that. So that's an interesting problem but as Brian said earlier, there's a lot of research has to be done in that.
Okay, I think we ought to wrap it up at this point. So first I'd like to thank you, the audience, for sticking with us for this panel. I think it's pretty obvious that we have an extremely bright group of very busy people who took time out to come here with us today and answer or attempt to answer a variety of questions, and we're particularly interested in any bright ideas that occurred to you regarding cross-fertilization between autonomous systems and the world of info technology. So if you have any great ideas, please send them to POCs that you get in the report at the end of the meeting, or if you want to grab somebody's business card, whatever. I'd also like to thank Melissa. Is that right? No, close enough. Okay, for sticking with us through some of the computer glitches we experienced. So, thank you all very much, and let's give our panel a final round of applause.